Welcome to today's video. In this video, we're going to work with the notion of a scalar product that we have recently introduced. And in particular, we are going to talk about orthogonal vectors. I hinted that we will use the scalar product, among other things, to talk about angles between vectors. And one especially important angle is the perpendicular angle. So we want to talk about vectors that are orthogonal, that have an angle of 90 degrees or pi over 2. And this is going to be the main topic of this video here. So the section is called Orthogonality. And we'll start with a formal definition of what orthogonality means for us. To be able to define orthogonality, we of course need a vector space and we need a scalar product. And usually in this chapter, we'll work with finite dimensional vector spaces only. Some of the things that we'll discuss extend to infinite dimensional vector spaces as well, but that's not going to be our main focus. So we'll usually just use Euclidean vector spaces here. And as always, if a general vector space is too abstract for you, just keep in mind all of this will usually be used in R to the n, and we'll see that in the examples later on. So let's say we have a Euclidean vector space, which is a vector space equipped with a scalar product. So let V be a Euclidean vector space. And the scalar product will, as usual, be denoted by angle brackets like these here. I will not make this explicit from now on. So whenever we have a scalar product, I will denote it in this way. Otherwise, I'll make a note about that. So let's introduce the notion of orthogonality. We'll start with two vectors. Two vectors will be called orthogonal if and only if their scalar product is 0. So two vectors, let's call them x and y, in the vector space V are called orthogonal if the scalar product of x and y is 0. We'll sometimes use a specific notation for that. Sometimes we will denote this by the notation x is orthogonal to y, like this. Then we can extend this notation a little. We can also define what it means for a vector to be orthogonal to a linear subspace. And the idea is pretty simple. We just say a vector is orthogonal to a subspace if it is orthogonal to every single vector in that subspace. So let U subset of V be a linear subspace. Of V. And then we'll say a vector x in V is called orthogonal to U if, and the condition is the scalar product of x and u is 0 for all u in capital U. And there is a notation similar to the one that we've just seen. We'll sometimes use the notation X is orthogonal to capital U, like this. And finally, the last stage of our definition here is two linear subspaces can also be orthogonal to each other. And in this case, the especially interesting case is the one of the orthogonal complement. So that means given a linear subspace, we can consider the set of all vectors that are orthogonal to all vectors in the given subspace. And this is called the orthogonal complement. And it will turn out this is again a linear subspace. So let U subset of V be a linear subspace of V. And then we'll define the orthogonal complement, which is denoted as U orthogonal, like this here. And it's defined as all vectors x in V, where the scalar product of x and U is 0 for all U in capital U. Okay, so this is what we call the orthogonal complement. Of U, and sometimes we need to stress the surrounding vector space V, so sometimes we call this the orthogonal complement of U in V. Let's see a few examples to get an idea of how this looks like. Now for the examples, we'll use the standard canonical scalar product in R to the n, usually R to the 2 for these examples here. So two orthogonal vectors, that's not that hard to see. So for example, we can use the vector, let's say 1, 2. And if you want a vector that is orthogonal to 1, 2, we just have to make sure that the scalar product of x and that vector is 0. So for example, let's use the vector y minus 2, 1. All right, so here we can take y. And then the scalar product here, that's the scalar product of 1, 2 and minus 2, 1. Again, standard scalar product in R2. So that means we have 1 times minus 2 plus 2 times 1. So minus 2 plus 2, that is of course 0. So that means x and y are orthogonal vectors. We'll also say the vectors are perpendicular. And that coincides with what we think of as orthogonal vectors usually. So if you make a quick sketch here of how those vectors look. Say we have x1, x2 here. Then the vector x, I'll draw this in orange. So the vector x is the vector 1, 2. This here. And the vector y is then the vector minus 2, 1. So that looks like this. That's y. And you can clearly see those vectors are perpendicular. So here is an angle of exactly 90 degrees. And that's what we think of as orthogonal vectors. So that coincides with the definition, of course. Second example, let's see an example of a vector being orthogonal to subspace. So for that, we just use a subspace in R2. Let's say we use the span of the vector 1, 1. That's the subspace of R2. Again, we'll make a quick sketch here. So that 1, 1 is this vector here. And then the span of this is this here. So that is U. That is 1, 1. And now we want the space, or want just one vector for now that is perpendicular to U. Well, one possible vector that we can use, for example, would be this one here. Right, so that might be a perpendicular vector. Let's call this X. And again, you can see there is a 90-degree angle in here. And the vector that we have found here, this vector X, that is minus 1, 1. Or of course, we can take a multiple of that one as well. So here, minus 1, 1 is perpendicular to U. Now formally, how would we prove that this is the case? Well, let's take an arbitrary U in U. Then we know U is the span of 1, 1. So every vector in U is a linear combination of 1, 1, or a multiple of 1, 1. So there exists lambda in R such that U is lambda times 1, 1. Well, that is the case. Then we can, of course, compute the scalar product of X and U. That is the scalar product of minus 1, 1 and lambda times 1, 1. And by bilinearity of the scalar product, we can take out the lambda here. So we have minus 1, 1 and 1, 1 times lambda. And now minus 1, 1 times 1, 1 in the scalar product. This is exactly 0. So we get lambda times 0, and this is 0. So that is actually correct. The vector X is perpendicular, or is orthogonal to U. So that completes this formal proof here. More general, if we have a linear subspace that is generated by a certain basis, then of course a vector that is perpendicular to that linear subspace needs to be perpendicular to each basis vector. And in turn, if that is the case, then it's also perpendicular to the space, because each vector in the subspace is a linear combination of the basis vectors, and we can then use, in the same way we did here, we can then use bilinearity to decompose that scalar product of X and an arbitrary U in the subspace into a sum of scalar products of X and the basis vectors. And if those are all 0, then of course the sum will also be 0. So just as a quick side note, more general, if B1 to Bn is a basis of a linear subspace U, then X is perpendicular to U if and only if the scalar product of X and each of those basis vectors is 0. So for all I in N. Let's see a few other examples. So let's see one for the orthogonal complement. First example is also in R2. So let's say we take the span of a different vector of 1, 3 this time, just to vary a little. So that's a subspace of R2. Make a quick sketch. So that's space 1, 3, like here, and also here. So let's try to draw this. Yeah, almost. So this is U. What is the orthogonal complement to U? Well, in this case, it's easy to see that the only vectors that are perpendicular to U are, of course, the ones that lie on this line here. So this should be the orthogonal complement. And again, you can see there is this 90-degree angle between those two. So we have two lines that are perpendicular to each other in this special case here. Right, so here we have U ortho is, in that case, the span of -3, 1. Right? In general, it's a little harder to compute that orthogonal complement, but we'll find a method that can do this very easily once we consider orthogonal bases in one of the following videos. Let's have one more example, just to show that this can also be done in higher dimensions, of course. Let's consider U to be the span in R3 of, let's say, the first two unit vectors. And that's just because it's easier to draw the vector space this way. Because, let's see, we'll take this one here, this one, and this one. And let's say this is x1, this is x2, this is x3. Then the vector space U here, that is created or is spanned by the first two unit vectors. So this is basically the plane as spanned here by those coordinate axes, the coordinate plane, the x1, x2 plane. Then what is U ortho? Well, all vectors that are orthogonal to this plane, and again, that will be a line. In this case, it's this axis here. Of course, that continues below the plane as well. So this here is going to be the orthogonal complement. So here the orthogonal complement is the span of 0, 0, 1. And you can easily see that each vector in the orthogonal complement is, of course, orthogonal to this and this vector. So it's going to be orthogonal to every vector in U, and these three vectors together span all of the R3. So that means there cannot be any more vectors that are included in U ortho and are not included in that span already. Finally, a little theory about orthogonal complements. As you can see in these examples, the orthogonal complement is actually a real complement, meaning that a linear subspace plus its complement together can span the whole space. Or in other words, if you have a vector, an arbitrary vector in that space, you can always decompose it into a part that is contained in U, for any given U, and a part that is contained in the orthogonal complement. So you can write it as a sum of two vectors, one in U, one in the orthogonal complement. And that's actually a very useful decomposition, and we'll make frequent use of that. So let's take quick note of that this works and how to practically compute that. I'll show you how to do that later on. So again, we'll have a Euclidean vector space, so vector space with scalar product. Let V be a Euclidean vector space. And this also includes finite dimensional, please remember that one. And let U subset of V be a linear subspace of V, then the following hold. First statement here is U ortho is again a linear subspace. So the orthogonal complement to a linear subspace is also a linear subspace. That's something that's not hard to check. You can just use the definition of the orthogonal complement and check that this really is a linear subspace. That's actually a nice exercise that you might want to do at home after you've completed this video. Second, the dimension of V, the whole space, is equal to the dimension of U, the subspace, plus the dimension of the complement. So together, the dimensions add up to the dimension of the original space. Again, that's because we have a complement. So those two together make up the whole space. And the third statement is to say what exactly it means to make up the whole space. What it means is for every vector V in V, there exist unique vectors. I call this U in capital U and U ortho in capital U ortho. So here the ortho just means a superscript to that vector. I could also have named that U star, yeah, just to get the correspondence. And those are the properties such that V can be written as the sum of U and U ortho. So it can be decomposed into a part in U and a part orthogonal to U. And this is called the orthogonal decomposition of V. It's something that we frequently use in engineering, for example. If you want to analyze a force, then what you often do is you decompose it into two parts. You decompose it into, for example, one part that is parallel to gravity and one part that is orthogonal to gravity. Things like that, yeah? So that often happens in applications, and we'll go into more detail of how to compute an orthogonal decomposition in one of the next videos. As a final remark, let's have a quick look at matrices and the spaces generated by matrices, how these behave with regards to orthogonality. Again, that's something that we will use later on. So let's take a linear subspace. Let U be a linear subspace of R to the N. And let's say we have a basis of that. So basis B1, B2, and so on up to Bk. And then we can, of course, define a matrix A, where those B's form the columns. So I'll write it in this way here. What I mean is the B's are the columns of the matrix. So with columns B1 to Bk. Then A is a matrix with n rows, because each of those vectors is an element in R to the n, so it has n entries. And we have k columns, so an n by k matrix. Well, why do we do that? Well, simply because this way we can express U as the column space of A. So we can always turn a linear subspace of R to the n into the column space of a matrix if we find that convenient. If we have that, then what can we say about the orthogonal complement? Well, the orthogonal complement consists of all vectors that are perpendicular, orthogonal, to all vectors in that column space, so to all columns of A. So a vector is in U ortho if and only if it is orthogonal to each column of A, which means it's orthogonal to each row of A transposed. Let's make a quick note here, right? So X is orthogonal to each column of A if and only if X is orthogonal to each row of A transposed. What does that mean? Well, that means that AI, or something is the B, is BI transpose X, so the BI transposed are the rows of A transposed. BI transpose X equals 0 for all I in 1 to k. Or in other words, the vector X is a solution of the linear system. X solves A transposed X equals the 0 vector. Or finally, in other words, X is an element in the kernel of A transposed. And that means the orthogonal complement of that space U, the column space of a matrix, is exactly the kernel of A transposed. And of course, we can also write this in the other way. We can also say the kernel of the matrix A. What is that? Well, that's the set of vectors that are orthogonal to each row. So that means we're talking about the set of vectors that is orthogonal to the row space. So this is exactly the same as the orthogonal complement of the row space. Okay, so this is the relation of column space, row space, kernel, orthogonal complements. Those are related via the orthogonal complement in a matrix. So you can describe finite dimensional subspaces of R to the n as column spaces or row spaces of matrices, and then the kernel of the transposed space would describe the orthogonal complement of that space. So, as I said, we'll go into the topic of orthogonality a little deeper in the following videos. In particular, we'll talk about orthogonal bases, we'll talk about how to compute an orthogonal basis and how to use it to compute an orthogonal decomposition later on. That's going to be the topic of the following videos, and I'm sure I'll see you then.